Hello. In this video, we're going to be looking at Ka and Kb of a weak acid and its conjugate base, or weak base and its conjugate acid. So let's get right in it. We have what is called the acid dissociation constant, Ka, and this is the equilibrium constant for the reaction of an acid with water, specifically a weak acid. So if we have some weak acid, Ha, it reacts with water. It's going to hydrolyze water to produce hydronium. And a minus our conjugate base. The Ka for this, we're going to include any species that is aqueous, gas, no liquids or solids, so we'll include hydronium, our conjugate base, and our weak acid. Okay. Now, looking at this, our dissociative form, where we're producing our hydronium, which is what makes an acid, right? That's on our right side, our product side, and on our Ka, that is on the top. So the larger the value of Ka, the stronger the acid. Okay? And we can kind of look at it another way, called pKa, where pKa is equal to negative log Ka. The larger this term, the smaller this term. So it's the same idea as pH and hydronium. So a larger Ka means a smaller pKa. Okay. So that's another way of looking at kind of the strength of our acid. Here are a couple of examples of some acids, going from really, really strong acids like hydrochloric and hydrochloric acid, which is an acid that technically has a Ka value. Anything stronger than that, the Ka value is just so large we don't even look at it. But we see that as we increase our strength, so going up this table, we increase the value of our Ka. But our Ka for a weak acid, so all of these down here, are still going to be less than 1. We can also see how pKa's are affected. So if we have a negative pKa, that means we have a strong acid. And then all of our weak acids are going to have pKa's that are increasing in value as we decrease in our strength of our acid. Okay, let's look at our base dissociation constant. So Kb is the equilibrium constant. For the hydrolysis of water by a base, specifically a weak base. Strong bases do not hydrolyze water. So we could look at it in two ways. Our base reacts with water to produce our conjugate acid. Plus hydroxide. So it produces hydroxide by reacting with water, or if we have a base that is a base based on it being an anion, it will also hydrolyze water to produce our conjugate acid plus hydroxide. So for the first one, our Kb, again, only aqueous species in here would be BH plus, OH minus, over B, and then our other Kb will be our HA hydroxide A minus. And same idea, the greater the value of our Kb, the stronger our base. Here are some Kb values for some weak bases. As a note, we can also solve for pKb. And the same idea. The larger your value of your Kb, the lower your pKb. Okay. Here is just a huge table with lots and lots of acids and bases in here. Remembering that if we have a strong acid, right, any of our strong acids, our anions from those strong acids would be negligible basicity, so they would not protonate upon throwing them into water. Then we have a bunch of weak acids in here that have weak base conjugates, and then we have very, very weak acids that come from the protonation of a strong base. Right, so let's look a little bit, kind of a summary of what we've talked about. So if we have a strong acid, it will completely transfer a proton. So it dissociates completely. So there is no molecular acid in solution. Okay. Its conjugate shows negligible basicity. If we have a weak acid, there is only partial dissociation. In water. Right, so we're going to have undissociated molecular acid in solution. Okay, and its conjugate is a weak base. And then the conjugate base of a negligible, so a species with negligible basicity, acidity, will form, or will come from a strong base. upon dissociation. Okay. Next thing, the stronger the acid, the weaker its conjugate base. Remembering that KW, or that KW is equal to KA times by KB. So as we increase our KA, we're going to decrease our KB, and vice versa. And then equilibrium favors the transfer of proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. So when we have an acid-base reaction, we're going to favor the transfer of a proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. We're going to have the greatest amount of weak acid and weak base. Okay, so our equilibrium will lie on the side of the reaction with the weaker pair. So for instance, let's take the following reaction where we have CH3COOH reacting with OCl minus, producing CH3COO minus plus HOCl. Okay. If we look at the Ka for our acids, so acetic acid has a Ka of 1.8 times 10 to the negative 5. HOCl is 3.5 times 10 to the negative 8. Acetic acid is the stronger acid. ClO minus, we have Kb equal to 2.9 times 10 to the negative 7. And then our acetate ion is 5.6 times 10 to the negative 10. So our OCl minus is a stronger base. So this side has a stronger species. So our equilibrium is going to be in that direction, towards our weaker species. So if we were to look at the K equilibrium for this, it would be greater than 1. Okay. So let's try a couple of examples of pH. So we've got a nitric acid solution. So we know that that is a strong acid. So when we take it and we throw it in water, it will completely dissociate to produce H3O plus NO3 minus. So all of this gets converted into this. So our HNO3 concentration will equal our hydronium concentration. So they both equal 0.025. So we can take our pH and solve for that very easily, giving us a pH of 1.60. If we have a strong base, it's pretty easy as well. We have NaOH. When thrown into water, we will completely dissociate. So our sodium hydroxide concentration will be equal to our hydroxide concentration. So when we do our pOH, it'll be equal to negative log 0.025. This gives us a value of 1.60. And our pH will be equal to 14 minus that number, which gives us 12.40. Okay. Now, let's move on to Ka calculations. If we have pH, we can very easily solve for Ka. We're going to use an ice table. Right? And what we're going to do is we're going to set up an ice table. After we've done that, we're going to solve for our equation, or solve for our hydronium concentration. Using H3O plus is equal to 10 to the negative pH. So if we have pH, we can put that in there. And then we're going to use our hydronium concentration to solve for X. Right? And then after you solve for X, you can plug in the equations, or plug in the concentrations into Ka. So, as a note, this can be done with Kb and pOH as well. Let's try an example. So we've got HF, which has a concentration of 0.250 and a pH of 2.036. We want to solve for Ka and pKa. So first, let's construct our rice table. So we start out with 0.25 molar here, and 0, 0, minus x plus x plus x. This gives us 0.250 minus x, x and x. Now we're going to solve for our hydronium concentration by taking our pH. Which gives us a value of 0.0092, 4 molar. And since H3O plus concentration equals X, we know that X equals 0.009204. So we can put this in for each of our concentrations. So HF is equal to 0.250 minus 0.009204, which gives us 0.241 molar. And then our hydronium concentration and our F minus concentration are both equal to X, which means they're equal to 0.009204 molar. We can then put that into our expression. Ka is equal to our products, hydronium times by F minus, so 0.009204 squared, divided by our HF concentration, 0.241. Which gives the Ka value of 3.52 times 10 to the negative 4. We can then solve for our pKa by setting equal to our negative log Ka. Which gives us 3.45. Okay, that's everything for this video. See you guys later.